Hi, I'm Jamie Batts, your instructor for AP2. We are continuing on with our lecture on metabolism and energetics. From chapter 23, we just finished talking about glycolysis. Let's start looking at lipids and how lipids are used in this process. Glycolysis was all about breaking a 6-carbon carbohydrate molecule down into a 2-carbon compound, which can then be used in the citric acid cycle and electron transport chains. But as we've reviewed already, several nutrients like lipids and proteins can also be converted into a 2-carbon compound to get energy. So let's switch here, get into it. So that's where we left off. Lipid digestion also begins in the mouth, just like carbohydrate digestion. We have the mechanical breakdown just by chewing and the presence of lingual lipase breaking those triglycerides down into monosaccharides and fatty acids. It continues in the stomach. Actually mixing the chyme with the stomach acid is creating very large drops of lipid-soluble compounds. So this lingual lipase is going to continue to function even in the stomach. It can only attack the surface triglycerides though, so not in the inner. So again, you have these big kind of globules, and the lingual lipase can only work on those outside parts. So only about 20% of the triglycerides are broken down here in the stomach. Lipid digestion is completed in the duodenum. CCK, that hormone, right, is going to trigger the contraction of the gallbladder. So what the gallbladder does is eject bile into the duodenum through the pancreatic ampullae, and the bile, the salts within the bile, break down the lipid droplets. It's a process called emulsification. Think of those like dish soap commercials where you see like Dawn or Palmolive like lifting the grease off of the pans. That's kind of how bile salts work in your duodenum, right? These big droplets are being dissolved, so to speak, or broken down into smaller parts by the bile salts. So CCK is also stimulating the secretion of pancreatic enzymes. So not just the bile from the gallbladder, but also the pancreatic lipases from the pancreas are going to come out and break those large triglyceride molecules down into fatty acids and monoglycerides and glycerol. So these molecules will form something called a micelle. Micelles are basically a lipid bile salt complex. So imagine this fat molecule that's basically surrounded by bile salts. It allows the fat molecule, which normally is insoluble in water, to be soluble in water. Does that make sense? So chewing, mixing, duodenum, CCK, bile salts, all that stuff. This is a nice summary of everything. So how does it get to where it's going? Well, that micelle, remember micelle is just the fat droplet surrounded by bile salts, is basically going to come into contact with the epithelium of our intestine and diffuse across our plasma membrane. When it does this, the bile salts are released, reabsorbed, and go back to the liver. This is that enterohepatic circulation of bile that takes place. The cells can actually synthesize new triglycerides from the absorbed lipids. So they take these lipids and can reassemble them. New triglycerides can actually be packed with something called cholesterol, which you may be familiar with, right? This forms something called a chylomicron. Cholesterol is kind of like a protein lipid byproduct. It's like a compound made of both proteins and lipids. So we take these newly formed triglycerides, we surround them with cholesterol, and they're now called chylomicrons. Chylomicrons are a type of lipoprotein, right? Lipoprotein, it's a lipid and protein. It's a little bit of both. Why do we have to make lipoproteins? Why can't these lipids just be absorbed just like glucose? Because lipids aren't soluble in our blood, right? Lipids can't dissolve like that. So we have to kind of put this outer coat on them, so to speak, a protein coat, to make them be able to be absorbed and dissolve. So it makes this chylomicron lipid soluble. These chylomicrons are secreted out of the intestinal cells through a process of exocytosis. They go into the lacteals, not into the hepatic portal system. Carbohydrates went to the hepatic portal system over to the liver. These chylomicrons go into the lymphatics. They're too large to go into our blood capillaries, right? So the lymphatic vessels carry them through the thoracic duct, dump into the bloodstream. There's enzymes in our capillaries called lipoprotein lipase It's breaking these chylomicrons down, releasing the fatty acids and monoglycerides, and the fatty acids and monoglycerides can then diffuse into all of the interstitial fluid and be used by all of our peripheral cells. So the cells that use these undigested lipids are skeletal muscles. Skeletal muscles like to use fatty acids to generate ATP. They get lots of ATP from fatty acids. Our adipose tissue will actually use fatty acids and monosaccharides to create triglycerides for storage, right? We all have some of that on us, right? And then our liver likes to absorb any extra chylomicrons, extracting the triglycerides and the cholesterol from the chylomicrons and recycling those parts. So here's the process in a nutshell. And here comes my daughter. Sorry. So, thank you, ma'am. Crazy girl. So, we have this, and I'm not sure why it's starting off with step number 4 here, but either way, we assume that it's already been digested, broken down. And I guess on those first 3 steps were on that slide a few slides ago when we talked about the lingual lipase and the pancreatic lipase that were being secreted. So we basically have these small lipid molecules that are going to be absorbed into our interstitial or into our intestinal cells in the form of a micelle once they're surrounded by bile salts. In the intestinal cells, they're converted into monoglycerides and fatty acids, and they can be combined with other cholesterol molecules to form this chylomicron. The chylomicron can be released and absorbed into the lacteals, right? From the lacteals, those chylomicrons go throughout the lymphatic vessels, eventually into the bloodstream, right? And then lipoprotein lipase in the bloodstream can break it down, and then our peripheral cells, like muscle cells and adipose cells, adipocytes, can utilize those FFAs, free fatty acids. So the liver can also absorb them. So absorbed chylomicrons from the liver are basically going to be disassembled. The triglycerides are going to be broken down. Cholesterol can be added and alter the surface proteins of the actual fat cell itself. This can either create low density lipoproteins or very low density lipoproteins, LDLs or VLDLs. VLDLs are going to transport these triglycerides to muscle and adipose tissue. So that's where they're going. LDLs take cholesterol to the peripheral tissues. The cells are then going to extract the cholesterol and use that cholesterol to build like cell membranes or hormones or any other material. So any excess cholesterol from this is going to go back into the bloodstream and head on back to the liver. So these are the good lipoproteins. These are helping our body build and restore and get energy from our fat. There's also HDLs that can be formed. These are special proteins that are released by the liver that absorb excess cholesterol that's in the blood and return it to the liver. The cholesterol is then used to synthesize more LDLs and VLDLs. It can also be used to synthesize bile salts. So all of these lipoproteins have a specific role. You may be familiar with bad cholesterol and good cholesterol. Overall, we say LDLs are the bad cholesterol. If we look back at this slide, what are LDLs doing? They're taking cholesterol to our peripheral tissues, right, so that they can be used in, building materials and such. But if you have excess cholesterol, excess LDLs, they're going back into the bloodstream and floating around, right? They can stick to your arteries and things like that if there's too much. So that's when it becomes a problem. You need LDLs, right? Everything in moderation. You need these molecules to do certain things in your body. But when you have too much, that's when it's bad. That's why LDLs kind of get a bad rep, but it's really having too many of them. That's bad. HDLs are so-called the good lipoproteins or good cholesterol. And that's because they're there to help absorb all of the extra cholesterol that's in the blood. So here you see the whole process continuing. So if those lipoproteins don't go to the skeletal muscle or adipocytes, they might go to liver where they're reabsorbed and forming LDLs or VLDLs. These VLDLs go to the liver and adipose tissue. LDLs go into the blood and peripheral tissue, and they can either be used to synthesize things for the cell, or they can be re-released and be soaked up by an HDL protein. The HDL protein will then take that cholesterol back to the liver for it to be recycled again. So we've alluded a little bit to implications in health or applications in health. Indicators of cardiovascular problems would be where you have a total cholesterol level of above 200 milligrams per deciliter. So, or if you have a high LDL to HDL ratio, in other words, you have too many LDLs per HDL, right? Because HDL is taking it out of the blood. And if you have too much LDLs, your HDLs, can only work so fast because you only have so many of them. So these values are basically showing you the generalized level of the cholesterol that's in your circulation. Most of the cholesterol that's going to your tissues is staying there instead of returning to your liver. Overall consequences include accumulating plaques in your blood vessels, causing heart attacks and strokes. Obviously very serious. I'm going to stop. No, I'm going to keep going because the next section is just on lipid catabolism. So you can pause the video here, go back and review these 3 sections. I suggest going back and resketching or drawing out, maybe even just simplifying those drawings, creating a flow chart of all of the processes, because the digestion and metabolism of lipids, or I should say digestion and absorption and utilization of lipids, was spread out over a number of different slides. So go back all the way to the beginning of this video where we talked about lingual lipase. That was steps 1, 2, and 3 on that slide, and see if you can put all of these steps in order, make a really big flow chart, or better yet, put them all in note cards and see if you can put them in order that way. So let's keep moving and talk about lipolysis or lipolysis. Same thing, just a different emphasis. Lipid catabolism is what lipolysis is. It's basically breaking down the lipids and converting those parts into pyruvate, or channeling them directly into the citric acid cycle. So some parts of the lipid can be converted into pyruvate and others are going to be converted directly into acetyl-CoA. It's much more efficient than glucose catabolism. Glucose catabolism is going to yield 36 ATP, whereas just 6 carbons from a fatty acid are going to yield 51 ATP. So it's a much more energy efficient process. And then you say, well, why don't we just use fatty acids for everything? Well, that's because our body needs fatty acids to build structural components like our plasma membranes, right? That's why our body chooses to use, or why our cells choose to use glucose as the main source of energy. We don't really use carbohydrates for much structure in our body. So we can use it for energy. If we run out of carbohydrates, then we're going to start using the fat. If we run out of fats, then we use the protein, and protein is the #1 component of your body. So we really, really, really don't want to use protein as our energy source. We'll get into that in a little bit. So let's talk about triglyceride catabolism. There's lysosomal enzymes within the lysosome, which break down these triglycerides into glycerol and 3 fatty acid molecules. Fatty acid molecules are broken down and converted into acetyl-CoA. It's a process called beta oxidation. Here's an overview of it. So you have your triglyceride molecule, which is basically a glycerol with 3 fatty acid tails absorbed into your cell. Your glycerol is converted directly into pyruvate. However, those fatty acid chains, look at how many carbons are on there, 18 carbons. Remember, we want to create a 2-carbon compound. So guess what? You have 3 18-carbon chains that are creating a 2-carbon compound. Do that math, right? 3 times 18 divided by 2. You get a lot of acetyl-CoA from just 1 triglyceride. That's why your body gets a lot of energy from fat. And that's also why your body stores energy as fat. So let's take a look at this. Once the acetyl-CoA and or pyruvate are created, the whole thing is identical to what we learned already in carbohydrate metabolism. Citric acid cycle, electron transport chain, oxygen is the final electron acceptor, all that is identical. It's just how do we get to pyruvate or acetyl-CoA, which is different. So here are the sub-steps and the whole process. Glycerol creating pyruvate, our fatty acid chains being broken down and creating acetyl-CoA. Picture this 18-carbon chain just basically being chunked off into 2 carbons by coenzyme A and forming acetyl-CoA. So there's also the process of lipogenesis. This is creating lipids. Why would our body do that? Well, maybe we have too much energy going on in our body. Maybe we're putting in too many carbs or too many lipids and we need to store it for later. So this is going to begin with acetyl-CoA. Almost any organic substance, lipids, amino acids, carbohydrates can be converted into acetyl-CoA. Some fatty acids cannot also be synthesized from acetyl-CoA. So this would be basically backwards of beta oxidation. Instead of the triglyceride or the fatty acids being broken down into acetyl-CoA, it's basically sticking acetyl-CoAs together to create a fatty acid chain. There are essential fatty acids. These are ones that cannot be synthesized from acetyl-CoA. These have to be obtained from our diet. These are linolenic acid and linoleic acid, or the omega-6 and the omega-3 fatty acids, which you may have heard of already, mostly in like dietary commercials and things like that. We also need to do lipogenesis when for particular things in our body, structural and functional proteins that are made from fatty acids. A lot of hormones are made from fatty acids, and of course our plasma membranes and cholesterol are made from fatty acids. So glycerol is synthesized from an intermediate product of glycolysis. When you put the fatty acids together with the glycerol, you get a triglyceride, which is our stored form of fat. So here is how these fatty acids can be used, either for energy or for structural components. The triglycerides can be broken down into glycerol and fatty acids. We already talked about how they're used. And then these compounds can be converted back into fatty acids. Pyruvate and acetyl-CoA can be converted into fatty acids, so that process of lipogenesis. Those fatty acids can then be converted into cholesterol, prostaglandins, phospholipids, glycolipids, steroids, right? Hormones, all of these little submolecules that we've talked about along the way in this course. Lipids obviously are used as an energy reserve. Why is this important? Because beta oxidation is very efficient. Your cells, again, like to use lipids as their energy reserve. They just need to use them for structural components before they use them for energy. So excess lipids are then stored. So your body's not going to use the lipids for energy unless there's a lack of carbohydrates. Your body is efficient at using fatty acids to get energy. However, it is not a quick process. It's much quicker to grab a glucose and create 34 ATP than it is to grab a lipid, break it down into fatty acids, and then do beta oxidation to get your 181 or so ATP from that one fatty acid. So it's not a quick source because it takes time for beta oxidation to occur. It's also difficult because our lipids are not water soluble. You have to find a way for water soluble enzymes to access all of these droplets. So it takes time for them to dissolve in the bile salts and be kind of malleable for these enzymes to work. Chronic energy demands during times of stress or starvation, or like marathon running or something that's kind of an endurance type event, hiking, something like that, would use lipids as an energy reserve. You can, actually I'm going to stop the video here so that you have a chance to review this section all about lipids. Our next section will go into proteins as an energy source. Have an awesome day.